It is Martin Drager here with Nilsen Giger on the webinar for practical applications of groundwater modeling in mining operations. So we are a very focused organization on solving water challenges across multiple sectors. We do have a team of professionals in earth sciences and in data management, including hydrogeologists, engineers, geotechnical experts, modelers, and we have a number of software engineers and data specialists. We started the company in 2017. In fact, Nilsen started it based on the demand for water resources services, particularly around mining. Now, if you don't know the name Nilsen Giger, Nilsen is actually the author of Visual ModFlow, a pretty much world-recognized software application that we use for looking at groundwater flow and contaminant transport modeling. In addition, he was the co-author of products such as Airflow SVE for soil vapor extraction, FlowNet Trans, and FlowPath. And he was the visionary behind HydroGeoAnalyst, which is a data management and subsurface characterization tool that has become quite a product globally. So the point here is this is a good opportunity for you to ask some questions of somebody who's been in the business a long time and has a great depth of knowledge, particularly around groundwater modeling. So starting in 2017, rapidly opening office the following year due to the demand from mines on our services. Later, and with the demand in minerals in general, in particular around energy minerals, we opened an office in 2022 in Kazakhstan, and then just this year in Waterloo, Ontario, strategically being close to all of our clients to make sure that our services and understanding of their needs are in alignment. Now, we do talk a lot about mining, and we should also acknowledge that we do service public and private sector clients in the water resources, water and sanitation, industrial and energy sectors as well. Now, in terms of our customer base, we'll just share a little bit about mining here. We're really proud of some of our accomplishments and milestones. You see here some key companies around the world that are actively mining, publicly traded companies, where we've helped them save a tremendous amount of time and money. For example, we helped a company save $40 million in annual costs with some data management and reporting solutions through our data management team. And we've also helped a 97% time savings in compliance reporting for another customer. And more relevant to this particular webinar is one of our clients saved $120 million in operational costs due to some optimization and dewatering that we helped them with. So we're really proud of this, and we look forward to working with many more companies in the future. Generally speaking, we have 6 core services: hydrogeology, hydrology, hydrogeotechnical, aqueous geochemistry, water audits, and data management. And now with ESG and global climate change upon us, a lot of effort is being put toward really gaining a deeper understanding of water. And so these core services are in high demand from our mining customers. And we're really fortunate to have a strong data management team that quickly helps us get digital information into a format that we can consume in the various service areas that we offer. So I won't go into detail around these services. You see it here. The main message is that why we're doing this presentation is we have a particular specialization when it comes to water resources management. We use groundwater models in a lot of the projects that we deliver. And the question then becomes, for mining operations, if there's too much water or too little water, where do they start and where can we help them? And Nilsen, I'll pass the mic to you. The floor is yours.
Thank you, Martin. Thank you for the introduction. And thank you all for being here. It's good to see a lot of known names. And I'm going to talk about a few practical examples that we have done recently using groundwater models to solve problems for mines. A lot of this work was done also by Karen Ninaner, who coordinates our modeling team, and she's here to help answer any questions as well. So let's start. Where do we start? Let's see. Water is very important, plays a very important role in mining, even though sometimes it's still not very valued by mining companies as it should. Water is used there are a lot of direct uses like mineral processing, water supply for operations, human consumption, tailings transport, dust, and indirect uses as well, that you need water to replace flows in the rivers, to replace water that's evaporated from reservoirs and so on. So one KPI that a lot of mines are using for sustainability is how many cubic meters of water is used per ton of ore produced. So coal goes from 15 cubic meters of water typically, and gold up to 250,000 cubic meters of water per ton of gold. And let's see the typical flow in a mine, solids. You take material from either open pit or underground mine. What do you do with this material? A lot of it is just where the ore is not. So it becomes waste rock. The waste rock, of course, produces some sediments. And the material that has some ore content that's worthwhile goes to processing. Part of that material becomes products, and part of the material becomes tailings and goes typically to mine tailings. Then water. Water, sometimes you need to dewater or to keep the underground mines dry. Part of that water can go directly to processing, or if there is more than needed for processing, it goes directly to tailings dams or to containment dams. Sometimes it's not enough water for processing, so you have to, or for mine users, you have to take from the environment other types of water. After processing, you may transport mine tailings to the tailing dam. You can reuse that water as well if you want. And then you have to treat this either wastewater from the processing plant or coming from the sediments or coming from the dam, and finally goes back to the environment. So where groundwater modeling plays a role, it plays a role in understanding hydrogeological behavior, risk assessment, mitigation. So you can do regional water resource assessment if you need water for operation, you want to know where to get it from. Then you can do environmental impact assessment. You can see how groundwater and surface water interacts. You can do operations in open pits, either by slope stability or dewatering open pits, underground mines. You can check the water table drawdown. You can calculate pore pressures as an input for slope stability. You can see the behavior of water in tailing dams. So you can have a lot of uses for groundwater modeling. Typical workflow for modeling. First, you have to get all the data, do a data analysis, hydrogeological assessment, build a very strong conceptual model, do your discretization, your model input, run the scenarios, implement whatever you're trying to predict and to implement. Then, of course, you have to do monitoring and keep doing. All of this need to be based on data. And model is the best thing. If you don't have data everywhere, it kind of does interpolation using the physical equations to simulate both flow and transport. So typical groundwater modeling options in the market. Of course, you have the ModFlow family with several pre and post processors. Those are the most common ones. And now they have several packages for ModFlow. Another strong package, V-flow, mostly used for mining because it has several advantages to represent fractures, complex geology, and so on. It has also applications for hydromechanical, for chemical reactions, and so on. Then there are the family of models that tries to use the complete hydrological and hydrogeological circle, like hydrogeosphere is one, and then you have Mike Shee, another one, and you have a whole family of other models. We're not going to cover all. For example, there's WinGW, ModFlow, one water hydrological model, and so on. So let's look at some practical applications. So let's see about sometimes you have too much water and you need to get rid of this water to make your mining operations efficient. You don't want to work on a mine with lots of water in it, open pit, for example, your tires go bad and everything. So you'd like to operate in as dry mine as possible. You also can cut your costs by doing that. There is a problem also that you may have flooding, halting productions. You may have social and environmental impacts by having a reduction of fresh water availability to local communities. You can enhance water stress in the areas. So models can be used to do that. So let's see this example here where we did a study to predict the advancement of the dewatering of open pits following the open pit plans, mining plans 2034, 2054. And then at one point, the open pit will intersect the groundwater table and it will change the subsurface flow and can change the base flow in the streams and so on. So what do you need to do? You have to do dewatering techniques to ensure as much as needed removal of water, but not more than needed. You can do hydraulic designs to mitigate impacts to base flow, for example, by replenishing water in the river. And you do continuous monitoring for groundwater level or flow rates. So first we need to define, to simulate the environment as it is today and identify where your open pit will intersect the groundwater table. And then the model can be used to answer what dewatering system will be applied. Is this technique the most optimized economic and social? So in this case, we use V-flow and simulation of different drawdowns. So we tried a combination of pumping wells, directional wells, sumps, horizontal trains. And this is typical, the impacted area of drawdown over the years. And this would be, for example, 2054, the final water level position after applying the dewatering. And then where the model was used, determining how many pumping and what's the location of these pumping wells, how much water it was pumped, and if the water level will be low enough so that the pit will be dry and also the slope stability would be guaranteed. So in this case, it's showing, for example, in 2024, that will be the location of the water table, the open pit. This is the end one. It was not there yet. In 2024, then that would be the location here. The model helped us to determine how many wells, the green line, how many wells were being used per year, and the total pumping rate that was used over the year prediction. So here we have the historical pump and a few more years, we would be pumping this up to reaching the current water take permit that the mine has. And here they needed to apply for a new flow rate permit based on this study. Also, the model was used to calculate not only the groundwater levels to keep the pit dry, but also if the pore pressure, in this case, FIFLO provides directly the pore pressure, if this pore pressure that was used as an input to a geotechnical model in order to guarantee slope stability. Then, that is close to the mine itself, operation. However, everything that you do in the mine will impact nature potentially. So in this case, same model was used to see the effect on the streams itself. So in this case, this is this point here, this spring, and the model was predicting that the stream would get dried after a few years. In this case here, these are the rainfall pattern, and we see the behavior of the flow rates at the springs would vary according to the seasons, but would not be dry and maybe possibly above minimum base flow we would like to keep. Then you can use scenarios to mitigate, for example, this spring drying. In this case, it was used an injection well close upstream of the spring, so the water table at this location were recovery and then spring would naturally show up again. After the mine closure, then what will happen? The water table is starting to recover. So here it starts to recover the center, and then everything goes up to a certain level. So this is the amount of in meters of how much water it went up, the water table went up. And this is the lake format. At one point, there is a discharge point where the lake is going to discharge. So what they wanted to do is to know how much discharge would occur, how much flow went to the pit, and then after it reached the discharge point, these would be discharging out, and they would like to calculate any hydraulic weirs or whatever they have to construct here to accommodate the predicted discharge rate at the exit point. Sometimes you are faced, sometimes with both, but sometimes you are faced with too little water. So you need water for ore processing, for wastewater treatment, dust control, human consumption, etc. And depending on where your mine is located, depending on how much water your mine is using, it may be enough water during one season, but not another. You may not be able to take as much water as you need due to regulatory constraints, competing usage, and also you have to be prepared to be resilient to any climate change with extended periods of droughts, for example. So in this case, it is a case in South America, in a dry area here between Chile and Argentina, and there is a future mine. There is a future mine that is located here. And here there is a lake, which is an environmental sensitive area, flamingo production. And the challenge was how much water the mine will be able to take water from this watershed. And if so, if the extraction of the water would affect this environmental sensitive lake. So a model was built, and the water table was calibrated with current conditions, and it was predicted where to take water from, in this case, from wells far enough from the lake where the base flow to the lake wouldn't be significantly affected, neither the water levels. And in this case, they were able to get permits to extract water for their operations. Another type of challenge, mine tailing deposition. So mine tailing deposition, it may cause some environmental contamination due to chemicals or metals leaking into the surface water and groundwater. Another thing is stability issues to avoid any failure of the deposition structure and to do the tailing management in terms of huge amounts of tailings they have. Typically, TSF, tailing storage facilities, are dams, dry stacking, for example, now more common filter drains, in-pit disposal, and underground backfill, underground mines where they do a backfill. We are going to show a case study for in-pit disposal. In-pit tailing disposal, deposition, has been more used since the failure of 2 dams here in Brazil. They have been using more the in-pit tailing. That becomes attractive because this practice can reduce potential environmental contamination. It's concentrating where the open pit was. It is cost effective since it does not require construction of new structures. And also, it helps even instead of just leaving this empty 200-300 meter lake, it can help the restoration of land surface and mine closure. So companies are looking more into it. And then you have typically tailings being deposited in this open pit. In this case, this is the simulation of the tailing evolution. As the tailing is being deposited, then also you want to calculate the recovery or the water table close to the tailing. Typically, when you are inputting tailing, let's say you have a dewatering system, the water table is low. You start to fill with tailing. You don't want to put the tailing on top of a lake. So you have to keep turning off the dewatering systems slowly, accordingly, so that the water table is always below, just below the tailing surface. And then you can use the models to predict and manage that, how you're going to turn off the dewatering systems according to the tailing filling. And then you predict the water table going up. In this case, this tailing was going to put here, there was a spring here, and they studied, it was identified this spring was very connected to the tailing. And in this case, also the study involved, after putting the tailing, optimize the usage of space and put a rock waste pile. In fact, rock waste and more tailing in between the big rocks, so that totally use this space. As you do the rock waste, 2 issues may come up. The environmental agents may ask, but if you put the rock tailings, you are going to increase the pore pressure underneath here. And 2 things may happen. You may activate fractures that were closed, and by increasing the pore pressure, would you activate pressure, the fracture openings here, and eventual contaminants may move to unknown pathways? That's one question. The other question is, what happens with the water that is here, and now with this extra pore pressure, it's squeezed out of the tailings? One positive effect is that the tailings has a settlement, and therefore you can fit more tailings than originally predicted. The negative effect is that where does this extra water go? So in this case, you have to apply a model that the traditional flow model is not enough. In this case, we use a plugin of free flow by AJMC, that the variables related to the mechanical behavior are incorporated in the formulation. So the pores decrease, the amount of water is squeezed out, and it's taken into account in the calculation. And also it calculates the displacement of the tailing. And we calculate the expelled water, and in this case, we're able to predict and prepare for any excess water that would come into the spring if you would need to take any measurements to mitigate our environmental impacts. Another use of models, groundwater contamination. Sometimes you have too much water, too little, or you can impact your quality, water quality. So that can create environmental degradation, can incur into remediation costs, you can have operational disruption, water supply impacts. So the plume may migrate. In mines, you have some chemical users that can cause that. Reactions may occur and create some mine drainage, acid mine drainage, but also even mine drainage that may not be acid, that may be harmful, and you can have spills and accidents. In this case, a particular case where we had a tailing dam, and the tailing dam was close to an environmental sensitive area, where it was a touristic area and very environmental sensitive. And it was determined that material from this tailing, the rainfall was recharging the tailing. In this particular case, the tailing was comprised of a specific material that not only it propagates a contaminant plume, which could be treated in a traditional transport model, but this plume, that plume reacted with the soil, this particular chemical, reacted with the soil, dissolving the particles of the soil, therefore enhancing the contamination issue, because it would basically create pathways by these dissolution channels caused by this material. So in this case, we had to use a chemical equilibrium model in order to calculate not only the traditional flow or plume transport reaction with decay and retardation, but also taking into account these different reactions. And then how to mitigate or to solve this issue. Two strategies. Well, let's put a pump and treat between the tailing dams and this, but there was this problem of we might even increase the solution of the material by attracting more water into this pump and treat barrier. Or another one is in situ precipitation of metals in the aquifer through the injection of reactants that help achieve chemical saturation of key minerals. So in this case, we have used FreakC. If you use mod flow, they have the PHD 3D package that is FreakC in 3D. If you use free flow, they have PyChem package. And there you can have thermodynamic reactions that, according to the change in pH, to the change of multiple reactions in the solids, in the soil, and the dissolved contaminants, what is the resulting composition of that water or the material. So in this case, we use that and use for optimizing remediation strategies and did that plume evolution. And in this case, two alternatives were tested: pumping wells, a hydraulic barrier, or injection wells. And the chosen effect was to have these injection wells of this reactant so that it will stabilize the plume by making that particular chemical precipitate. And therefore, instead of opening more pores, it would actually help to clog the pores to stop the advancement of the plume. And finally, Also very common because of the dam break, especially the upstream dams. A lot of dams now built on the upstream mode, they have to be decommissioned. And therefore, you need to have this plan. Like when you're decommissioning, you may remove the tailings, and during the removal, you need to know how to dewater. You may have to build superficial surface drainage construction. You may impermeabilize. So a typical example, you have this tailing dam, and by decommissioning it, you change the topography here, you do some capping, and then you end up decommissioning the dam, leaving it more stable than a dam with this slope. You end up making much smoother slope. And also then you have to the surface, you have to know how the groundwater behavior will be here, given the various scenarios that you can do. So we use that as well. In this case, sometimes very important that you end up knowing the heterogeneity within the tailings itself, because that may play a big role if we have tested case where you have homogeneous material assumption or heterogeneous, and it may cause some big surprise if you don't take the heterogeneities. You have to be able to represent very well the drainage structures within the dams itself. So you should use a model like FIFLOW or any structural grid mod flow to be able to represent things not only vertical in a stair-shaped case, but actually as close as possible your property here. In this case was 3 dams that had to be decommissioned. So first type was to understand the hydrogeological behavior, where it was, the water table definition, degree of saturation, and the hydraulic gradients. And then 2 different scenarios for decommissioning this dam and see where the water table would be, what are the pore pressures, the effects of impermeabilizing the bottom, impermeabilizing the top on the system itself. Sometimes you have to keep active dewatering systems to get rid of the water, like in this case, the decommissioning included the maintenance of pumping wells here to lower the water table and still guarantee the stability of the slope. And then sometimes you have to do everything integrated, because you do this, but then you say, what if over the years there is some reaction happening and the clogging of the drainage systems? Then how it will behave. So then you have to have flow, you have to have chemistry, and you have to have geotechnical all integrated working together, which is a big difficult because usually mines, geotech and hydrogeology still work very more separate than they should. But we're trying to change that. And you can understand the future hydrogeological behavior of these dams. And also, in this case, for example, you do the dam, everything works fine. But you say, what is the maximum rainfall probability, for example? And then in this case, it came, okay, if it rains for X number of days, and the last few days it rains a lot, then what would be the behavior? This would be the typical behavior of the water table in a certain system. But in this case, if this event happens, the water table goes up 1 meter, which may make a big difference in the stability here, or overflowing your dam. So you can use that for understanding with different, to see if it's resilient in terms of climate change. With that, we finish the presentation. I would be welcome to answer questions that you may have.